And we are ready for round 2. So today's lesson is on part 2 of the gas laws, meaning, y'all, there's some more gas laws here for us to learn. We'll be learning about Avogadro's, the combined, and the ideal gas law. Since these gas laws are all mathematical equations showing the relationship between things like P, V's, and T's, we will, of course, need our calculator for when we get into some practice problems that we'll be working together. But let's see, what are these new gas laws going to tell us today? Regardless, in any gas law, guys, these are these important things that we need to remember. All temperature units must be in Kelvin for any gas law problem. If they give me Celsius, you're going to add 273 to convert it to Kelvin before you do anything else. All volume units need to be the same on both sides. Does not matter what they are. All pressure units need to be the same on both sides. It does not matter what they are. We know that STP, or standard temperature and pressure, is equal to a temperature of 273 degrees Kelvin, or 0 degrees Celsius, and 1 atmosphere of pressure. And finally, if you need to convert units, do not round anything until the very, very end when you get done to the end of the calculation. So these are a repeat of some of the rules that we've been kind of consistent with so far. How does this apply to maybe these new gas laws that we're going to be learning about today? It's still about the PVs and T's, you guys, but now we're going to throw in some ends. So these next 3 gas laws actually incorporate the number of moles. Our previous gas laws, we were not messing with the number of particles in my gas. We were looking at the same amount of a gas under changes of pressure, volume, and temperature. But here, I'm going to maybe give us the ability to increase or add more gas or take it away and see how that maybe does affect some of the other stuff going on here. So these first 2 gas laws that we'll learn about today are going to show how an ideal gas is affected by a change in conditions. We know this is showing a change in conditions because I see 1s on one side and 2s on the others. That means my initial conditions and then my final conditions, okay? My last gas law that we're actually going to be learning about, I don't see any 1s and 2s. I only see 1 of each letter of the alphabet. Okay, this last gas law is going to show an ideal gas behavior at only 1 point in time. So that's the main distinguishing factor about this last gas law called the ideal gas law. I'm not looking at changing conditions. I'm just looking at 1 point in time. What are the properties of the gas behavior showing me? So our first gas law today is Avogadro's law. Avogadro is looking at how the number of moles of a gas and how its volume are related. And yes, you guys, this is the exact same Avogadro who developed the concept of the mole, meaning 1 mole of anything in chemistry is equal to 6.02 times 10 to the 23rd particles. So Avogadro is doing a lot of work for us today, not only with the concept of the mole, but now with his law. This will have a mathematical equation, but Avogadro's law also describes just in generally what I can expect the relationship between the number of moles and volume is. He makes this statement. His principle states that equal volumes of gases, as long as they are at the same temperature and pressure, will contain an equal number of moles. So look at Avogadro here. He's looking very smart. He's got 3 balloons of hydrogen, nitrogen, and oxygen. He is saying, y'all, these balloons all have the same volume. And this means, as a result, they will contain the same number of molecules. So this is a wild statement to make because it is regardless of the type of gas used. The type of atom or molecule that makes up these gases does not matter to me. Nitrogen is very different than oxygen, is very different than carbon dioxide. There are different letters of the alphabet representing different elements that are involved in here, right? Well, as a result, those will all have different masses depending on what their mass is, right? But at the same temperature and pressure, if the volume of any of these gases are the same, the number of moles and therefore the number of particles will be the same as well, as long as you are at the same temperature and pressure, which is really cool. Okay, so let's run through this scenario. I have 3 different gases. It looks like I have argon gas, I have oxygen gas, I have nitrogen gas, right? And they're giving me some information about the gases' volumes, masses, quantity, meaning the number of particles, and pressure and temperature. It says which gases in the picture contain the same number of particles as 1 mole of a hydrogen gas would. You're like, what are you even talking about here? Well, y'all, let's look at some of this data. Specifically, what I'm noticing is the temperature and pressure are the same. I am at a constant temperature and pressure between all three of those samples. I'm like, cool. Looking at the volume, I notice at that constant temperature and pressure, they all have the same volume. Oh my gosh, they also all have the same number of particles here. They have the same number of moles. So y'all, all three of these samples of gases all contain the same number of particles, and they will have the same number of moles because they have the same volume at the same temperature and pressure. A lot of sameness going on here. What is different though is their masses, because they are different particles, right? Now, here's something that was a throwback to one of our previous units. 1 mole of any gas at STP will have a volume of 22.4 liters. This is known as the molar volume of a gas. According to Avogadro's law, if I have two different gases at the same temperature and pressure, if they have the same number of moles, they will also have the same volume, okay? Now, if that temperature and pressure is standard temperature and pressure, we can further state that 1 mole of any gas is equal to 22.4 liters, which is the molar volume of a gas. So constant temperature and pressure, equal volumes are equal numbers of moles. Now, mathematically, what does this also mean? It also states this. V1 over N1 is equal to V2 over N2. Remember, the N's in chemistry represent the number of moles, okay? So this is an initial conditions of a volume and the number of moles, and my final conditions of a volume and a number of moles. So this is allowing us to change the number of particles in the sample of gas we are studying. Specifically, this states that if I increase the number of moles, meaning if I add more gas particles to my sample, I will have an increase in volume. That makes a lot of sense. More stuff in there means you're going to take up more space. Or if I take away or decrease the number of moles in my sample of a gas, it's going to decrease my volume. Now, this statement is only if pressure and temperature are remaining constant here. So in my picture, my sample with the fewer number of dots, the fewer number of particles of moles, is obviously going to take up a smaller space, and the more particles I get in there, it's going to take up a greater amount of space. So let's look into this a little bit further.
We're now going to study Avogadro's law. Avogadro's law is simply the relationship of the number of moles of gas being proportional to the volume in which they occupy. Once again, we've got our piston and cylinder picture, but this time it's a little different. We have a side on it where we can pump in more gas or remove gas. We are going to keep the pressure and the temperature exactly the same during this, and that is one of the criteria for Avogadro's law. As you can see from this illustration, we have a certain number of particles floating around inside this system. If we pump in more gas, and you could do this like with a bicycle pump, as you put in more moles of gas, the volume is going to increase proportional to that number of moles. So it's very simple. Whatever your volume is with 1 mole, your volume will be double that with 2 moles, and it'll be triple that with 3 moles. That is Avogadro's law, the direct proportionality of volume and number of moles. And as you can see here, we have a simple equation to help remind you of that. Volume over moles in one state equals volume over moles in the other.
All right, so we've got another direct relationship here between some properties of gases. This is a direct relationship between the number of moles and the volume that those gas particles will take up. We know a direct relationship graph shows a slopey slope up, which indicates as I increase the number of moles or the number of gas particles into my sample, the volume will increase, meaning it'll take up more space. So let's see some demonstrations of Avogadro's law in action.
Acetic acid and sodium bicarbonate react in a 1-to-1 ratio to produce carbon dioxide. Let's do each of these reactions and compare the sizes of the balloons. First, 4 grams. Next, 8 grams. $16 grams. and 32 grams. In these two flasks, the sodium bicarbonate was the limiting reactant, so it could only produce as much CO2 as it had sodium bicarbonate. This flask, the 16-gram flask, is the stoichiometric ratio, so this is a perfect 1-to-1 ratio. In this flask, the acetic acid was the limiting reactant. These should be pretty much the same because they had the same amount of acetic acid, so that's all that could react.
Y'all are like, oh man, I never thought I'd hear the term limiting reactant again. And yes, don't worry too much about that. But I do love that the first 3 balloons showed that as you increased the number of moles of the reactant, you would obviously increase the number of moles of the gaseous product that was produced. I saw as the number of moles of gas increased, they took up more and more and more space, right? That final balloon did not increase more in volume because the limiting reactant part of the reaction equation ran out to where that volume did not change from that point. But yeah, more moles means more volume. So let's actually use this mathematical equation to see if we can solve some problems with Avogadro's law. So I'm going to bounce down to the document camera. So we have our fun little Avogadro's law right here showing the direct relationship between the number of moles of a gas and the volume of a gas. Okay, our problem says a balloon filled with 0.020 moles of a gas has a volume of 0.48 liters. Some of the gas is removed, giving the balloon a new volume of 0.24 liters. How many moles of gas are left? Okay, well the first thing I'm going to do is I see some numbers in my problem. I like to circle my numbers in my problem and then identify them in terms of, well, what are you? Are you a P, V, T, or an R, or an N now? Well, moles, you guys, that's my N. Yes? Liters is a volume. Liters is another volume, okay? So a balloon initially had this starting amount of moles. So this is my N1. That's my initial number of moles. And it took up a volume of that. So that was my initial volume, my first volume. I am removing the gas, okay? Giving the balloon a new volume of 0.24 liters. This is my second volume or my final volume, okay? So they're asking how many moles of gas are left. So I'm solving for N2, okay? So this is our first gas law where I'm allowed to take moles out or put moles in, and what I've done here is to remove some. So we want to know how much are left when it reached that new volume. So my equation is V1 over N1 is equal to V2 over N2. I'm using this to solve for my N2, right? Got to check and make sure my volumes are in the same units. They are. They're both in liters. If they were not, I would have to convert to some similar unit, right? Now I'm ready to substitute in. My initial volume was 0.48 liters. My initial number of moles in the sample was 0.020 moles. And my final volume was 0.24 liters. I'm solving for the number of moles. So with solving mathematically, what I like to do is my baseball bat in baseball, to where the guys that are on the crossway are my baseball bat, and the guy that is not, he is my ball. So I'm going to multiply together the baseball bat and divide by the ball. So when I get my calculator out, I'm going to multiply both of these guys together and then divide it by the 0.48. So in my calculator, I have 0.02 times 0.24 equals, and I'm going to then divide it by the 0.48, and I get this. Okay, let's have a sig fig conversation. I have got to round my answer, since this is multiplying and dividing, I've got to round my answer to the value in my problem that has the least number of significant figures. Looks like everybody in here has 2 sig figs, so my answer must also have 2 sig figs. What my calculator gives me is 1 sig fig. So to create 2 sig figs from this, I've got to add a 0 to the end. So my number of moles is going to be 0.010 moles. Okay, so does this math prove Avogadro's law? Let's see. What I've done here is I have decrease the volume. Well, in order to decrease a volume, that would mean I would have to remove some of my gas. So hopefully the number of moles has gone down. Yes, it went from a 0.02 to a 0.01. So that is the proof that we need for Avogadro's law. So let's see what our next law is to learn for today. This next gas law is so satisfying. This next gas law is called the combined gas law for a very obvious reason, because I'm combining P, V, T, and N all together into one law. So it's wondering how all of these various things are related. Y'all are not ready for this. Boom. So this law combines 4 gas laws: Boyle's, Charles, Gay-Lussac's, and Avogadro's principles. Those are the 4 laws we have learned so far. You guys, in the full form of the combined gas law, it looks like this. P1 times V1 over N1 times T1 is equal to P2 times V2 over N2 times T2. Y'all are like, what is even happening here? The way the combined gas law works is, if you'll remember, we've been saying a bunch of things being like, well, this is the relationship between these two things as long as temperature is held constant, or as long as volume is held constant, or as long as the number of moles is constant. When I say something is held constant, that's like me covering it up in the combined gas law. Whatever you have not covered up is the gas law that you are looking at. So remember when we talked about Boyle's law, which was P1 times V1 is equal to P2 times V2? Only looking at the pressure and volume. That was me assuming that the number of moles was not changing and the temperature was held constant. So if I cover those up, y'all, Boyle's law appears to me. If I'm making the number of moles in the pressure held constant, the only values that are left are the volume and the temperature. That's Charles's law. If I'm keeping constant the number of moles and the volume of a gas, P and T is left. This is Gay-Lussac's law. If I'm holding constant the pressure and the temperature, that's Avogadro's law, you guys. So the combined gas law, you don't even have to remember all of these ding-dang equations. If you remember just this one law, all of the other ones are hidden in there because you can pick them out depending on what is held constant and what is changing. Very, very cool. Now, the most common way you'll see the combined gas law written is this way, okay, where you do not have the ends. That most of the time when we use the combined gas law, we're keeping the number of moles consistent anyway, so where we don't have to have that featured in our equation. So we use it to measure the behavior of a sample of gas with a constant number of moles under a change in conditions of P, V, and or T. So let's look at some example problems of us using this combined gas law, right? Once again, we will not be using the number of moles for all of these examples. The number of moles will be held constant. Now, of course, if I give you information and they're letting you know, hey, the moles are changing, you can use N. But typically, this is the iteration of the combined gas law that we tend to see. So the first one, let's see. It says a quantity of helium occupies a volume of 16.5 liters at 78 degrees Celsius. And I'm already overwhelmed with the number of numbers in this problem. I'm gonna go ahead and start circling some stuff, you guys, because this is like a lot going on. Oh my gosh. So I've got a 16.5 liters. Liters is a unit for volume. I've got 78 degrees Celsius. Celsius is a unit for temperature, but whoa, I've got to make sure that I change the temperature to Kelvin by adding 273 to see what my first temperature is. So 78 plus 273, and I get 351 Kelvin, right? And then I have a pressure, and atmospheres is a unit for pressure, so this is my first pressure. Oh my gosh, so I have an initial volume, an initial temperature, and an initial pressure. I've got a lot of letters of the alphabet, which means I'm using the combined gas law to incorporate all 3 of those. So what is the change that is happening? It says, what is the volume at STP? So I'm going to be solving for the volume, the V2. You were like, well, how am I going to find the P2 and the T2 then? STP gives me some information, you guys. STP gives me a standard for a temperature, which we need another temperature, and a standard for a pressure, which you guys, we need another pressure. This is amazing for us. We've got everything that we need. This lets me know at STP, my T2 is going to be 273 Kelvin. And my P2 is going to be, well, what's our units for our first pressure? Might as well keep them the same because they need to be. Well, it's in atmospheres. Well, great. At STP, the pressure is 1 atmosphere. All right. Assume the number of moles of helium remains constant. So this is what I'm talking about. Remember when we say assume something is constant, that means we get to scratch it out of our equation. That is not a factor that we are going to be observing changing conditions. Okay, so it is constant over time. All right, so we got a big old beefy equation to hang out with here. We got P1 V1 over T1 is equal to P2 V2 over T2. We are using this equation to solve for V2. Got lots of numbers to fill in. All right, our substitution, we have 45.6 ATM. Our volume is 16.5 liters. And our first temperature is 351 Kelvin. Yes? Our second pressure, because we're at atmosphere, is we're at STP is 1 atmosphere. We're solving for V2. And then our second temperature at STP is 273 Kelvin. Oh my gosh, how am I supposed to solve this problem? We can still use the baseball bat and the baseball, you guys. I just have a much longer baseball bat, which would require me to multiply 3 numbers together, right? But now I've got actually 2 baseballs here. This one was the one that we were typically used to seeing, but now I've got a second baseball that is actually right next to the variable that I'm trying to solve for. Y'all, no matter, I just have to divide by both of those, okay? So mathematically what I'm gonna do in my calculator, I go 45.6 times 16.5 times 273, right? So that's my baseball bat. And now I'm gonna divide by 351, and I'm gonna divide by that 1, right? So that's my answer. So we have solved for the second volume. The second volume is 585.2, but rounding for sig figs, everybody in here has 3 sig figs. I want to have this conversation about STP values. I wrote those values in there. They did not see exactly 1 atmosphere. So that is going to be what is understood to be infinitely significant, since I had to produce those O numbers just from the statement that we were at STP. So I'm not looking at that and being like, oh, we won sig fig. I made that up, okay? I just put the number 1 there and did not continue on with point any zeros. Okay, so everybody else has 3 sig figs. So I need to round this to 3 sig figs. So I have 585. Well, what are the units for this? Well, my first volume's units were in liters. So my second volume's units must be also the same in liters. So a little bit more numbers involved in here, a little bit more math. We can still use our baseball bat and baseball strategy, except we have a couple of more balls here to juggle, if you will. Okay, we've got one more practice problem with the combined gas law. Let's see what is going on here. It says a pocket of gas is discovered in a drilling operation. The temperature of the gas is 480 degrees Celsius. You're like, yikes, Celsius, but that is my first temperature, right? So my first temperature, I need to convert that to Kelvin by adding 273. That means it will be in Kelvin, 753 Kelvin. And its pressure is 12.8 atmospheres. So this is my first pressure. Then it says at the surface, the same gas has a volume of 18.0 liters. Y'all be careful. They are saying that this is a new condition for this gas. So this is actually my second volume. Okay. And that second volume of a gas will have a pressure or a temperature of 22 degrees Celsius, which in Kelvin is 295. And a pressure, so those are T2, and a P2, the pressure is going to be 1.00 atmospheres, okay? Okay, so I've given you all of my values of my condition after it has changed, right? So they're saying how large was the pocket of gas? How large is a size? They're wanting to know what the volume of the pocket of gas from the initial conditions were. So here I'm solving for V1. Assume the number of moles of gas remains constant, which means, y'all, N is not a problem for us. So I'm using the standard version of the combined gas law without the N's. They're being held constant. Okay, so we have P1 times V1 over T1 is equal to P2 times V2 over T2. I'm using this to solve for V1, okay? So we have some substitution. My pressures, my first pressure was 12.8. Atmosphere. My first volume is what I'm solving for. My first temperature, they said in Kelvin, was 753. My second pressure was 1 atmosphere, or 1.00 atmosphere. Making sure that your pressure units are the same on both sides. They are, which is good. My second volume was 18.0 liters. And my second temperature was, lots of numbers in this problem. I'm like trying to search and find. Okay, it's going to be 295 Kelvin. This is why labeling all this stuff is very, very helpful, because it's like you get overwhelmed and lost with all the things. Okay, so I'm solving for V1. So I got to take the baseball bat that runs catty corner or crossways along V1. And I'm going to multiply all those numbers together. And I've got two baseballs, this one down here and this one down here, that I'm going to divide that answer by. So my calculator comes up to help me out here. And I'm going to have on my baseball bat, what is it, 753? Times 1, I'm just going to write times 1 even though it's irrelevant, times 18, right? So that's my baseball bat, and then I'm going to divide by these two balls. Divided by 295 and divide by 12.8. So my answer is this. V1 is equal to 3.5 blah, 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 blah. How many sig figs? Everybody has 3 sig figs. So I'm going to round my answer to 3 sig figs, which means it is 3.59. The units for this volume are liters, because my other volumes units were also liters. Cool. So this was the original volume of that gas at that initial temperature and pressure. So combined gas law is it's got a lot more numbers, but that is not a big deal. We can totally just look at them and identify whether the units are a unit for a pressure, volume, and temperature, see what PVs and Ts we have assembled, and see what it is that we need to solve for. Okay, last gas law, you guys. And our last gas law is the ideal gas law, okay? Ideal gas law has all of these letters in there, P, V, T, and N, but it shows how all of these are related for a gas that is not under changing conditions, which is really cool. Let's see. PV equals nRT is your ideal gas law. This is the mathematical relationship between pressure, volume, temperature, and the number of moles of a single gas at one point in time. Like if I were to take a picture of a gas and figure out what its pressure, volume, and temperature and number of moles is, that is what this equation is showing me. It's not undergoing a change in conditions of some initial to some final, like pretty much all of the other gas laws we've learned so far. It assumes the gas behaves as ideal, just like all the other gas laws. I don't know why this one specific is called the ideal gas law, but this is, the other ones are also for ideal gases. The cool thing that I find about the ideal gas law is all of the other gas laws, they have been able to create this one ideal gas law. So let's see how this equation was derived.
What leads to the ideal gas law? It's really just a combination of all the laws we've put in place so far. Boyle's law, Charles' law, Avogadro's law. You put all those together and you will ultimately end up with the ideal gas law. So let's start with Boyle's law. Boyle's law is pressure times volume is a constant. And we've got that here now, with pressure times volume is a constant. Now we're going to bring in Charles' law, where volume over temperature is a constant. So we simply add a T to this problem in the denominator. Now we've got what is classically known as the combined gas law. Pressure times volume over temperature is a constant. We now add in Avogadro's law, which is simply putting an N for the number of moles in the denominator. And now we've got pressure times volume over temperature times moles. All of that equals a constant. But this time the constant is rather special. This constant has a name. We're going to change it from K to an R. And the R is the universal gas constant, which has a specific value. If you choose to use, which we mostly do, liters and atmospheres and Kelvin temperature and moles, then the value you get for R is 0.08206 liter atmospheres per mole Kelvin. And that's what you use in a lot of your ideal gas law problems. There are other versions of R, and it's important to keep that in mind. So use the version of R with the type of problem you've been given, or if you're happy with this version of R, make sure you always convert everything into liters, atmosphere, Kelvin, and moles. That's the ideal gas law, and it works over and over in chemistry so many times.
So that's our ideal gas law, and it is probably the most common gas law. It is definitely the one that we will be using the most, even in further units where we're not technically focusing strictly on gases. But the key thing about the ideal gas law, y'all, I have to have these units for pressure, volume, moles, and Kelvin. All the other gas laws we learned so far, we were like, Kelvin, it must be Kelvin. The other ones, who cares, as long as they're the same on both sides. But no, here, my pressure, it's got to be in atmospheres. My volume has to be in liters. N has got to be moles, okay? And the reason for that is because R is a constant, and that constant's unit of liters, atmospheres over moles, Kelvin. That's what allows for you to use the numerical value of 0.0821. So I've got to be watching out for some units here. So let's go use this ideal gas constant and our ideal gas law and see if we can determine some of the properties of a gas at one point in time, not under a changing condition. So here I go. First one, and I wrote up here just so we have it visually here what our R constant is. Pressure needs to be in atmospheres, volume needs to be in liters, N is moles, and then T, of course, is Kelvin. Okay, so question number 1. A 1.7 mole sample, ooh, we're getting excited, N of CO2 gas at 4.0 atmospheres, ooh, it's a P, atmospheres is P, occupies 17.3 liters, ooh, liters is a volume. What is the temperature of the sample? Solving for T. Now, if you'll remember, like especially when we did some combined gas law stuff, I was labeling 1s and 2s. Well, here I got to a spot and I'm like, I did not even find a repeated letter of the alphabet here. Okay, when I see one of only one letter in my equation, I'm like, that's got to be the ideal gas law. I'm not dealing with a change in conditions. I'm just looking at one gas at one point in time. So I'm using my ideal gas law. I'm like, cool, PV equals nRT. I'm going to be solving for temperature. So what I like to do with my ideal gas law, what feels comfy for me, is to go ahead and rearrange my variables to get it to say T is equal to whatever mathematically is required. So T would be equal to, I've got to put N and R underneath PV. So PV over N and R. So now I'm going to be on unit alert. We know my pressure in the ideal gas law needs to be in atmospheres. Is it? Yes. We know my volume needs to be in liters. Is it? Yes. We know moles needs to be moles. Is it? Yes. So I'm actually good to go. Actually do not need to convert in any way. Okay. So my pressure is 4.0 atmospheres. My volume is 17.3 liters. The number of moles was 1.75 moles. And my gas constant is 0.0821 liters, atmospheres over moles, kelvins. I know it's super duper annoying, but that tells me that I need to check all of my units for everybody else in there as well, or else it will not work out. So to calculate, I have 4 times 17.3 divided by 1.75 times 0.0821 equals, boom. I'm not going to look at the ideal gas law constant, meaning R. I'm not looking at that for sig figs, but everybody else, yes, absolutely. Okay, that guy's got 2 sig figs, that's got 3, and that's got 3. Uh-oh, he only has 2 sig figs, so that limits me, which means my answer needs to be rounded to 2 sig figs. So that means the temperature here is going to be, oh, you can barely see, 480. I have to stop after that 8. Just do not put a decimal behind the 0 or else that would be leading it to be significant. What are the units? Y'all, temperature is always Kelvin, but also we would know that if it's coming out of the ideal gas law, we got some units we need to have. And for temperature, it's specifically Kelvin. So this is me using the ideal gas law for a not changing condition situation, applying all of my moles, pressures, volumes, and temperatures together. One more ideal gas law problem, and then I think we'll feel real good about it. How many grams of O2 gas occupies 22.4 liters? Ooh, I have a volume at 50 degrees Celsius. I don't even know what gas law I'm about to use yet, but I do know that I do not like Celsius, so I will add 273 to that and turn that into 323 Kelvin and 3.3 atmospheres. That is a pressure. What are they asking me to solve for? Grams. Grams. We don't got mass in none of our gas law problems. We do not. But I can also look here and be like, how many V's do you have? Well, I just have 1. How many T's do you have? I just have 1. How many P's do you have? I just have 1. I'm not looking at a change in conditions. The only gas law that is not looking at a change in conditions is the ideal gas law. And so you were looking at, like, well, grams is not in here. Well, I've got everything else but in moles. Well, I'm going to have to solve for moles, and then I can convert it to grams. You're like, oh my gosh, that is so exciting. I can do that. Yes, you can. So what we can say is we can say solve 4 moles first. All right, so we are using PV equals nRT, solving for moles. So rearranging that equation to say moles is equal to would be PV over RT. So I got to check out to make sure everybody's units are looking good. Pressure, is it in temperature? Pressure, is it in atmospheres? It is. We're good. Volume, is it in liters? It is. We're good. Temperature, is it now in Kelvin? It is. We are good. So we are good to go. My pressure was 3.3 atmospheres. My volume is 22.4 liters. My R constant is 0.0821. The units for that are liters, atmospheres, moles, Kelvin. And then finally, my temperature in Kelvin is 323 Kelvin. Okay, so calculating things out, I've got 3.3 times 22.4 equals, divided by 0.0821 and 323. Okay, so that's what my calculator gives me. I'm like, how many sig figs do I need to round this to? And we're going to stop right there. We're not going to round yet. We're going to keep this number in the calculator if you would like to write your rounded version down here, but that's not my final answers. This is giving us moles. We're going to take it to grams. I don't want to stop it off too short to where my answer is slightly altered from what the final answer in grams should be, okay? But this is a good conversation on we're going to hold things in our calculator until we're ready for them. So I do have, looks like 2 sig figs coming from my pressure. So I'm going to say 2.7, and that is where I would stop. But I'm going to, just for the sake that this is notes, I'm losing some pencil lead. Just for the sake that this is notes, I'm going to kind of indicate that we're not going to round yet in our calculator. So don't round yet. Okay? But this is how many moles I have. Okay, so I'm going to take this now and I'm going to put it into a unit conversion, and I'm going to convert this from moles into grams using the molar mass of maybe oxygen. So I have some space up here, and I'm going to say that was 2.8 moles of oxygen. We know for every 1 mole of oxygen, the molar mass of oxygen is 32 grams, right? So that number is still in my calculator. I know I shortened it there just so I did not have to write all of those numbers on my page, but now it's still in my calculator to where I can mathematically just say that number times 32. So that is a more precise or a more accurate number from this calculation because I did not incrementally round. Okay, so now that's my answer. Now this is the answer I can officially commit down to putting on my paper, and it's 2 sig figs. So I have, it looks like, to 2 sig figs. I'm running out of space. We're just gonna write it up here. 89 grams. Yes? So that's cool. So the idea of the ideal gas law is it allows me to, through moles, be able to convert from grams. It would also allow me, if I gave you grams, you could convert that grams into moles first and then put it into the ideal gas law to solve. So there are a lot of gas laws. They all have a lot of P's, V's, T's, now N's. Let's kind of like summarize what all we have learned this unit in terms of these mathematical equations. And here they are. Y'all, we have learned a lot. How many laws is this? 1, 2, 3, 4, 5, 6, 7 laws. You're like, how can I even remember? Well, first of all, you guys, a lot of these laws are all the iteration of this big, giant combined gas law, right? We know that if we are holding any one of these things constant or more than one of these things constant, if we remove them from the equation, the other gas laws will reveal themselves, right? Do not forget about Dalton's law of partial pressures. This just says that the total pressure of a mixture of gas is equal to the sum of the individual gases' partial pressures, okay? And then the ideal gas law of PV equals nRT is our last one that we learn, where you're not undergoing a change in condition. So it's really only like 3 gas laws. Little Dalton's law here, where you add up stuff. The big old combined gas law, which has got a lot going on in here. And then my ideal gas law of PV equals nRT. So these are the gas laws. They help show us how gases behave in terms of their pressures, volumes, and temperatures, which is how we study gases.